So, for your last lesson in AB Calculus, which is kind of exciting, we have to do L'Hopital's rule. So here's some information. It was actually developed by Bernoulli, so we should give him the credit. L'Hopital paid for lessons from Bernoulli and then published Bernoulli's work. But, that's too bad. Oh well. We're still going to call it L'Hopital's rule because that's what you're going to know it as. Okay, so here's the thing. My English. If I asked you to find this limit, right? So take a minute and write that down. Pause the video. Before using L'Hopital's or before knowing L'Hopital's, the only way that we could do this, so first you should always plug in the value that x is approaching. So I've got 2 squared minus 4, which is 0 over 2 minus 2, which is 0. So we get 0 over 0, which is actually an indeterminate form. If you were to get 0 over, say, 5, then the answer is 0. If you were to get 5 over 0, then the answer is either negative infinity or positive infinity because it's a vertical asymptote, and you need to figure it out. Is it going up or is it going down by plugging in numbers approaching it? But because it is 0 over 0, we actually can do a different thing. Now, algebraically, I can still work this out. Limit as x approaches 2, and I have the numerator, which is the difference between squares, x plus 2 times x minus 2 divided by x minus 2. Those can go away, which means graphically we have a hole, which we should remember that from rational functions if you have 0 over 0. There's a hole in the graph, and in actuality, the function looks like x plus 2, the function x plus 2. It's just at 2, and in fact at the point 2, 4, there's a hole. And so here's what we can do. We can just plug into what we're left with, and there's the limit. Okay? Even though it doesn't exist, that's what it's approaching. So here's the thing. L'Hopital's rule is actually kind of interesting because what it allows us to do, and there's a proof for it, and I'm not going to go through it because I'm not going to take that time. You can actually just take the derivative. It's really kind of interesting, but the limit as x approaches 2 of f of x divided by g of x is equivalent to the limit as x approaches 2 of f prime of x divided by g prime of x. L'Hopital's is the only time when we're taking limits and you get indeterminate form, either 0 over 0 or infinity over infinity. This is the only time that you are allowed to take a derivative of a fraction by taking the derivative of the top and taking the derivative of the bottom and calling it good. Every other time you better use a quotient rule. So here's the thing, let's prove it. Or let's at least see that it works in this case. So limit as x approaches 2 of the derivative of the numerator is 2x, and the derivative of the denominator is 1, and if I plug in 2, I get 4. And there we go. So if you're working a question on the AP exam and it looks like this, you can absolutely use algebra to simplify it out and to find your answer. A lot of times they like to use a's and b's instead of variables, so they might be like x squared minus a squared over x minus a, and then that would be the limit as x approaches a. Okay? You can still work it out, x plus a times x minus a divided by x minus a, limit as x approaches a. Those go away, plug in a plus a is 2a. Okay? So you can still do that, but you can also use L'Hopital's. So if I were to take the derivative of the numerator, I would get 2x, and take the derivative of the denominator, I would get 1. We're taking the limit as x approaches a, and again, I get 2a. Okay? But the other option is you get problems like this. This is actually what you're supposed to recognize as the definition of the derivative. Okay, limit definition of a derivative. So way back when we were all younger in August, I taught you that if you take the limit as x approaches, or no, let's do h, as h approaches 0 of f of a plus h minus f of a all over h, then that is the same thing as the derivative of f at a. Okay, so let's talk about what our function is. This form right here, so h is x, so if I replace all those with an h, let's see if that makes sense. A, it looks like it's pi, so if a equals pi, then I'm trying to find the derivative of f, and I think in this case, f is going to be cosine of x is the original, because we're going to plug a plus h in for x. So f of x versus f of a plus h, which means f of x is just cosine of x. So this is saying find the derivative at pi. Find f prime at pi. Now let's make sure this also works. F at a, so that's f at pi. Cosine of pi is -1. And it was minus that, so that's +1. That makes sense. Okay, so it is definitely the formula. Let's prove it though. If I find the derivative of cosine, I get negative sine. And then if I plug in pi, I get negative sine of pi, which is 0. Okay, so I know my answer is 0. But that's for me knowing that the derivative of this is, I mean, I took this really, you know, I really thought it out and stepped it out. But in actuality, I would expect you to be like, okay, function is cosine, find the derivative of pi. Derivative is negative sine, plug in pi, there we go. Cool? But I was trying to talk it out with you. Let's go ahead and apply L'Hopital's. Although, I gotta make sure L'Hopital's works. So limit, I'm gonna rewrite it, as x approaches 0 of cosine of pi plus x plus 1 divided by x. So I'm going to plug in 0 for all the x's, okay? So I've got cosine of pi plus 0, which is cosine of pi, plus 1 over 0. Cosine of pi is -1, -1 plus 0, or plus 1 is 0. 0 divided by 0 is indeterminate, which means L'Hopital's applies. It only applies if you end up in one of these two indeterminate forms, 0 over 0 or infinity over infinity. Or some other ones, but you don't have to worry about those. All right now. So I'm going to take the derivative, limit as x approaches 0. The derivative of cosine of anything is negative sine of that thing, pi plus x, times the derivative of the interior, which is just the derivative of x, which is 1. The derivative of 1 is 0, so that's gone, and the derivative of x is 1. So if I just plug in x into this expression, x equals 0, then I get my answer. And sure enough, if I plug in 0 for x, then I get negative sine of pi. And pi is over here on the unit circle. And sine is 0. So that's 0. Okay. So a couple different ways to work this. One, recognize that you get L'Hopital's, which or you get the indeterminate form 0 over 0. If you get 0 over 0, then you can apply L'Hopital's, take the derivative of the top, take the derivative of the bottom, and then just plug in. But the other option is a problem like this, you recognize it as a limit definition of the derivative. And then just work it. So let's practice some problems. Alright, well this is just the definite L'Hopital's rule. If you want to take, if you want to write anything on your pink sheet, then I would write like, instead of writing, well maybe write indeterminate and then write 0 over 0 or infinity over infinity. Then that's what I would do. Okay. So let's do this one. Limit as x approaches 0 of 1 minus cosine over x plus x squared. First you have to establish that L'Hopital's rule is necessary for this, okay? So you must plug in what you're approaching and prove that you get one of the indeterminate forms. So if I plug in 0, I get 1 minus cosine of 0 over 0 plus 0 squared. Cosine of 0 is 1. 1 minus 1 is 0. So I get 0 over 0, which is indeterminate. So if I were doing this on the AB exam on an FRQ, I would write L'Hopital's. And then actually some books even put an S with there. Hospital? The hospital? I don't know why. I think there's 2 different spellings. But I think the AP exam actually does use S, but whatever. Okay. So I'm going to take the derivative of the numerator and denominator. So the numerator, the derivative of 1 is 0. The derivative of negative cosine is positive sine. The derivative of the denominator is 1 plus, and the derivative of that is 2x, okay? So if I plug in 0, then I get sine of 0, sine of 0 over 1 plus 0. Sine of 0 is 0, so I get 0 divided by 1, which is 0, okay? Now here's the thing. If I kept going, if I took the derivative of this again, I would get cosine, that would go away, and that would be 2. So cosine of 0 is 1. My answer would be 1/2. But that is not the answer. The answer is 0. Okay? That's the only way that I can work this problem. I can't algebraically maneuver this until I can simplify it. So I have to know to use L'Hopital's, 0 over 0, use L'Hopital's, take the derivative. I don't get 0 over 0, which means I have to be done. 0 over 1, answer 0. 1 over 0, positive infinity or negative infinity, I gotta figure it out. But let's practice on where you do. Keep going. So on this one, we're going to take the derivative. Well, first we're going to plug in 0. And it's not 0 that you have to be plugging in, it's just whatever you plug in, you get 0 over 0. So if I plug in 0, I get the square root of 1 plus 0 minus 1 minus 0 divided by 2 divided by 0 squared. I get 1 minus 1, which is 0, minus 0 over 0. I get the indeterminate form 0 over 0, which means we're going to use L'Hopital's. Okay, so we're going to take the derivative. Now I'm going to remember that this is 1 plus x to the 1/2 minus 1 minus 1/2 x over x squared, and that's the form I'm going to think about when I take the derivative. So, limit, still as x approaches 0, of the derivative of this is 1/2 1 plus x to the negative 1/2 times the derivative of the interior, which is 1. So, just as a reminder, the derivative of the square root of something is 1/2, and then the square root of it in the denominator, right? 1 over 2 square roots of 1 plus x. Yeah? I'm going to go ahead and write that, but whenever, well, I'll come back to it. So 1 over 2 square roots of 1 plus x. The derivative of negative 1 is 0, and the derivative of negative 1/2 x is just minus 1/2. Divided by the derivative of x squared, which is 2x. So that's an issue, because I'm going to have 0 in the denominator, but oh well. Alright, let's plug in 0. So we must plug in 0 every time we take the derivative. Plug in 0, I get 1 plus 0, which is 1. This is 1/2 minus 1/2, which is 0. And 2 times 0 is 0. That's indeterminate form again, which means I can use L'Hopital's again. If you're going to use it, you got to make sure you tell them what you're doing. We're using L'Hopital's. So limit as x approaches 0. I'm going to take the derivative again, only, like I said, this is the derivative, this is the form, but that's what I'm going to use to take the derivative, so I'm going to remember that this is 1/2 1 plus x to the negative 1/2. So when I take the derivative, I bring the power down to the front, I get negative 1/4, and then 1 plus x to the, subtract 1 from the power, negative 3/2, or 1 plus x to the 3/2. In the denominator. The derivative of negative 1/2 is 0, divided by, and the derivative of 2x is 2, so that's promising because I no longer, I'm definitely done using L'Hopital's because my denominator cannot in any way be 0. So, well, just kidding. I guess if I'm dividing by a fraction, this fraction up here could have 0 in the denominator and 0. So if I flip and multiply, it's still 0. So I was just kidding. Alright, so if I plug in 0, I get negative 1/4 divided by 2, which is over 1, which means multiply by, 1/2. And I get negative 1/8, and that is my answer. Because when I plug in 0, I get 1 plus 0, which is 1, and 1 to any power is 1. Except for infinity. And there we go. Here's your homework. That's L'Hopital's. I'll be available tomorrow, Wednesday, the 18th, for questions over this or for volume, cross-sections. You got the cross-sections homework. That's going to take some time. I might post some solutions on that, but I will definitely expect to be hearing from you guys and to be talking to you about these problems. Okay.